Okay, hello, good morning, everyone. I see so far there is nobody here, but I'll be recording anyways, okay? Because I have to have another appointment at 10:30, around 10:30, 11 that I need to leave. So I will start right on time. And for those who are answering later, you can just see the lecture, okay? I'm gonna share the recording later. So let me share my screen.
Bom dia.
Bom dia. All right, so we've stopped here. Okay, so Lucia, can you see me? Can you see the lecture?
Yes.
Yes, okay, all right, fine. So we stopped there where we've seen so far the basic ingredients for dark matter pheno and cosmology. We have reviewed the Boltzmann equation for the number density of particles for Bose-Einstein statistics and Fermi-Dirac statistics. They are both proportional to the temperature to the third power. And we also noticed that they are really related to each other apart from some constant which we defined as G effective, which takes different values depending on the statistics that the fermions obey. Okay, and we also did the same exercise for the energy density for fermions and bosons, but they are rather proportional to the temperature to the fourth power. And then later I went through cosmology and derived the relation between entropy density, energy density, pressure, and temperature. And as radiation fields and matter fields obey different equation of states, then the entropy that those fields exert in the universe are different. Therefore, and we realized from that only radiation fields contribute to the entropy density of the universe, and that's very important. For instance, in the radiation dominator era, where photons drive the expansion rate of the universe, therefore the entropy density is just dictated by photons. There's also some contribution from neutrinos, which is subdominant, but still we can account for it because the photon temperature and the neutrino temperature are related. Okay, and also, okay, let me go back, go down. And also we derived, so everything so far was for the relativistic case, and we also saw in the end of the last lecture the case for non-relativistic particles, which experience a Boltzmann suppression on their masses, okay? So the number density of particles are exponentially suppressed, and the energy density is just the number density times the mass of those particles. That's what we used, okay? And also we've seen some ingredients from cosmology. I'm just reviewing everything again so you can keep everything in mind for the things that I'm gonna say today. We also derived the fluid equation, which dictates how the energy density evolves as a function of time. And then that was the very end of our last lecture. We derived the abundance for hot relics and for cold relics. For hot relics, we just used the yield defined as the number density over the entropy density. And then we realized for the case of neutrinos, which decouple around at 1 MeV, that the number density, the abundance of those neutrinos is proportional to their masses divided by 100 eV. And then we concluded that using data from Planck and other telescopes, the sum of the neutrino masses should be below 1.1 eV. Therefore, neutrinos are too light to be the dark matter of the universe. And we following up to that, we covered cold relics, discussing that the freeze out happens when the expansion rate is roughly equal to the expansion rate. It's just an approximation. We need to really fully solve the Boltzmann equation to derive the decoupling temperature. But just using some standard definitions for the number density, we concluded that let me go back here. That's the picture. That's, I think, is emblematic in this case because you can really see what's going on. Where in the with the black curve, I plotted the square root of x exponential minus x, where x is the ratio between the mass of the particle and the temperature as a function of x. I'm just plotting a function, okay, exponential function. That's all. But I overlaid with green and pink the curves at which this function results into a value for different cross sections, because when you impose that the direction rate is equal to the expansion rate, that function, the exponential function, is related to the cross section, to the annihilation cross section of the particles that are experiencing annihilation processes and expansion. Therefore, so the freeze out temperature will occur where those two curves, they intercept. So at around 30 or 50, so that would be the value for the x variable. So the x variable, remind you again, that's the ratio between the mass and the temperature of those particles. Therefore, x should be around 30 and 50. And the conclusion we arrived last lecture was that the regardless of the model you're considering, the freeze out temperature or the freeze out parameter x will be roughly the same by a factor of 2. So even if you consider different models, dark matter models, hidden sectors, whatever, the moment at which the freeze out happens is merely the same. Okay, so that was key to our last lecture. And based on that, like a consequence of that comes the WIMP miracle. The WIMP miracle refers to the miracle. Miracle is not really a miracle. I'm gonna try to advocate this. So they call it WIMP miracle is because since the freeze out happens roughly at the same time for different models, therefore the dark matter abundance you get for a cold relic is roughly the same regardless of the model you have. But however, I do not see this as a miracle. That's my personal view, because we had as premise thermal equilibrium. So thermal equilibrium, not the freeze out. Thermal equilibrium is actually that what established the relic density you get. So it's not being a model. So I don't care which model you have. Once you enforce thermal equilibrium, you already are tuning your model in such a way that you can get the right relic density. So that's the key premise, is thermal equilibrium, not the model itself or not the freeze out itself, but the thermal equilibrium. The thermal equilibrium dictates the rest. So that's the key assumption in my opinion. So the dark matter abundance, or the abundance for a cold relic, is simply the ratio between the density of that species divided by the critical density. When you compute that for the case of cold relics, the ratio you get simply depends on the number of particles that freeze out. But now, since we haven't covered that in detail, that's what I'm going to do it right now. So let's go slowly now. So the abundance parameter is the rho. Rho is the energy density of that species divided by the critical density. And as we've just seen, the energy density for a non-relativistic particle is the mass times the number density. So that's what it is here, divided by the critical density, where chi, in my case, is the dark matter particle. So my dark matter particle is experiencing some annihilation, okay? Annihilation to some whatever. Whether it's nanometer particles or some dark sectors, doesn't matter. But has to have annihilations, okay? It ought to have annihilation. However, at freeze out, then I have the number chi at freeze out. Today, I have n chi naught, which refers to today. So the number density of dark matter particles today is the number density today divided by the critical density. But the number density of particles today, I know how to compute it, okay? We've just seen it, whether it's relativistic or non-relativistic, but in our case, we are focusing on non-relativistic at the moment. So what you can see here, what I did is from that, go back. So I have the mass here, and then this row critical density, and then I just multiplied by T naught to the third power and divided by T naught to the third power. And what I'm calling here n chi at T equal T naught is I'm just calling n naught. So n naught refers to the number density today of those non-relativistic particles. But we've seen, so there's a typo here. We've seen with n and n that the Comovin entropy density is constant. Therefore, as the entropy density is proportional to T to the third power, then I conclude from this equation that T to the third power times A to the third power is equal constant. In other words, A times T is equal constant. Why I'm using this? Well, I'm going to plug in this conclusion right here and back in this equation above, okay? And I sent to Clarissa already these lecture notes, okay? You all have that in PDF. Not with all those remarks, but it's fine. Everything's there. Okay, so in other words, I can relate the number density at a given temperature to the number density at a different temperature, to whatever temperature I can think of. Then I just play with this relation to rewrite the dark matter density in this way. So what you can conclude from that is that the dark matter abundance is proportional to the freeze out, x is equal mass over the temperature at freeze out, the number density of particles at freeze out, temperature at freeze out, and the temperature of photons today. We saw that way up there in the last lecture that the number density is proportional to this. Number density without the F is temperature without the F, max Planck mass times sigma. Sigma is being the annihilation cross-section. Then I picked which time. So I'm picking at freeze out. So freeze out, freeze out. I could pick it today and today, whatever. Why I'm doing this? Because n freeze out is exactly the function that appears there. And then again, I play with the equations to find this final formula. So the temperature today of the photons today, I know from CMB. The critical density I also know. The Planck mass I know is a constant. The cross-section I don't know. Depends on your model. And the freeze-out temperature, which I know is roughly 30, 20, 40, whatever. Within a factor of 2 is the same thing. So roughly speaking, I can rewrite this equation as this. Plug in the constant values, and then I arrive at this final formula. Now you're going to see why people call this a Wimp miracle. So you see, I need omega matter today according to Planck's 0.3. So for dark matter, let's say if I want a total abundance of 0.3 or 0.2, so roughly speaking, what I need is Well, I do know that the X freeze out is roughly 20 or 40 within a factor of 2. So it won't be far from 40. And the cross section should be around 10 to minus 8. GV minus 2. So I just converting centimeter squared to GV. Okay, so let's see what this number looks like in the standard model theory. So the cross section being 10 to minus 8, GV minus 2. However, that's the number we picked to get the relic density right. But we know that for cold relics, well, I know the velocity of the stars in our galaxy. The velocity of the stars in our galaxy are non-relativistic, and they are roughly c/3. Okay. So what happened is even if you pick velocities of being c/3, okay, being not quite relativistic but close to it, or even if you take 10 to minus 2 c, pick this one. Even if you pick v roughly, which is the correct value, 10 to minus 2 c, or in some, depending on the object you can consider in 10 to minus 3 c, or v equals c/3, either one of those values, what you're gonna find is that the sigma, if you take a velocity which is close to c by 1 order of magnitude, or by 2 orders of magnitude, or by 3 orders of magnitude, you're going to find that the annihilation cross-section, not just the cross-sections, the annihilation cross-section to me is sigma times v, v being the relative velocity between the two particles. So let's say one's at rest and the other one is moving, so v is the relative velocity. Okay? So you get the sigma v is 10 to minus 26. Now, just from this discussion I mentioned, you can see, for instance, one of the assumptions which is often overlooked. So when people come with Merkel, they say this cross section, 10 to minus 8 GV minus 2, leads to the correct thermal relic. That's not quite right. So as you see, in all books, all textbooks, they assume that the V is roughly c/3. Well, if V were actually c/3, what you're saying is that dark matter is roughly relativistic because it's not very far from C. But okay, you plug in this number and you get the sigma V 10 to minus 26 centimeter cube per second. So, however, dark matter is not relativistic at all. So even if you pick and put the value 10 to minus 3, C is already 3 orders of magnitude away. So this number being 3 10 to minus 26 is not like, you have to take it with a grain of salt. So it's not a solid number, okay? It's just an order of magnitude estimate for the sigma V, which gives rise to the correct relic density. So let's recap. The ring Merkel refers to a case where particles that have cross sections around 10 to minus 8, they all lead to the correct relic density, regardless of the model. So this is a miracle. Whatever model I can think of, if it's cold relic gives the right relic density, well, sure, it gives you the sort of the right relic density because from the very beginning you started with the thermal equilibrium assumption. Then it's a consequence of that. It's not that, okay, now you find it, wow, what a surprise. No, you started with thermal equilibrium. And then as a consequence of that, you're going to get the relic density, which is in the ballpark, the correct ballpark. Okay? So this number here, 10 to minus 26, happens to be, or 10 to minus 8 GV minus 2, happens to be precisely the cross sections that often appear in the standard model. For instance, if you do E plus E minus W plus W minus annihilation, that's the cross section you get of the outside the resonance. Outside the Z resonance, that's what you get, around 10 to minus 8. If you do E plus E minus going to E plus E minus outside the resonance, that's what you get. So what the miracle is saying is, that, okay, so perhaps dark matter particles have cross sections around the standard model scale, which I know how to detect, which I have measured. I have won Nobel Prize in terms of that. So means that, okay, I can perhaps really discover dark matter using standard model processes. However, again, in my opinion, to me does not come as a surprise, because all the standard model particles were in thermal equilibrium. So if you start with thermal equilibrium again, sure, you're going to arrive at the same annihilation cross section. The key difference is the abundance of the standard model particles is very far from the one from dark matter. So despite having the same annihilation cross section, they do not lead to the same correct relic density. And there is a reason for this. And the reasons for this because dark matter has continued to be stable throughout the expansion of the universe and experienced the freeze out. Okay? So despite having the same annihilation cross section, the dark matter particles experience a freeze out much later. Okay? So if you compute the abundance of the standard model particles, the freeze out temperature for them occurred, like, I mean, very early on. They were relativistic at the time. So the abundance they had are very different. So when you solve the Boltzmann equation, they are very different. And another point is important to emphasize that the abundance of the standard model particles have to all be embedded in the BBN. What I'm trying to say is all baryons, all matter has to account for around 5%. And E plus, E minus are baryons according to cosmology, right? So they have all to be within this 5%. So for instance, when you compute QCD, when QCD happened, hundreds of GeV. When the phase transition of the standard model, hundreds of GeV, that's what I meant. The W plus W minus, when it came out of equilibrium, much, much earlier. So, and they do experience interaction, which are not just weakly interactive massive particles. They do couple to photons. They have very different processes. The only processes that have just weak interactions are neutrinos. All the other ones experience other interactions, except for the neutrinos. But neutrinos happen to freeze out at 1 MeV. If neutrinos froze out, I don't know, at much later in the expansion of the universe, let's say not 1 MeV, maybe keV or something, much later, their abundance would be different. Okay, but they froze out at 1 MeV, and as a consequence of that, we find that relation between omega is sum of the mass of 100, which is suppressed. So the key aspect of dark matter is that it does not possess electromagnetic interactions, do not experience strong interactions, and they are stable. Okay, and they are very massive. So I think they are like neutrinos, heavy neutrinos that decouple at different times. Basically, that's what they are. Okay, heavy neutrinos that decouple at different times. And because of the evolution, the yield goes like this. You get a very different abundance. Okay, so that's the freeze out is. So you do not specify the model concretely, but you still find the correct thermal relic, the correct abundance if you have an annihilation cross-section around 10⁻26. But again, as I said and emphasized, you get this correct relic abundance if you start with a thermal equilibrium process. Okay? If you depart from thermal equilibrium, this is no longer the case. So to me, this is not a miracle. Okay, so now are there any questions for the moment?
I think this label was needed to get some buckets building.
It was to sell the idea. Basically, that's what is it. So let me next time for questions, because I'm going to move to the other one. Hold on. Okay. So the third lecture has to do with the Boltzmann equation. Okay. So the Boltzmann equation is simply an equation that determines how the number density of particles evolve in terms of your space, whatever your space is. In the space that we will be considering is the time. So L would be the Liouville operator that describes the change in the phase space, and the collision term, which determines how the number density changes with time. This obviously was named after Joseph Liouville, who was a French mathematician. So this F function is a distribution function. It's just a space phase that we know, for instance, from particle physics or statistical mechanics. We learned this the integral in the momentum space. That's what it is, F function. So there's a question. Lucia?
Hey, Professor, are you presenting the slide?
No. Você está mostrando os slides? Okay. Now you see?
Sim, yes.
Okay. Okay, so going back, what I was saying is this guy is the collision term, and this guy is the Liouville operator, which determines how the change in the phase space happens. This collision term, as you're going to see, is related to the number density of particles. So I will not derive all the formulas because there are lots of pages here. You can see all the notes, okay? So I derive explicitly, solve explicitly the Boltzmann equation. So I leave it to you as an exercise. And you should hand it to me. So I'm going to already tell you that is a list, a homework. So that's very easy homework. You should send to me by Friday 2 things. First is the abundance of cold relics, solving the Boltzmann equation like I did in the last lecture, and the hot relics. And again, now solving the Boltzmann equation in a more professional way, which that's what I'm going to do today. Okay, so you have to send it to me by Friday if you want to, well, if you want to receive a certificate of the school.
So it's 3 exercises.
Yeah, 3. 1 for solve the Boltzmann equation. Well, solve the abundance for hot relics. That's what I did for neutrinos. For cold relics, that's what I did in general. I just finished reviewing it. And the one's really solving the Boltzmann equation as I'm going to do it today. Okay, it's just reproducing the notes, basically. Okay, so it's not just me speaking. You have to get your hands on it. Okay, so what you do is, I won't go again through the details of the Boltzmann equation, so it's up to you, it's your task to review all this. So what I want to emphasize is the following. In the end, what I have is something related to phase space and something related to n, which is the number density as a function of time. So the number density as a function of time, well, it depends on the expansion rate of the universe. Okay, so I have to plug that in. Okay, and the phase space, which depends on the momentum of the particles, also depend on the expansion rate. So as you can see here, the number density of particles will depend on the expansion rate. Moreover, the number density of particles will also be affected by the annihilation rate, because the more I annihilate, the fewer particles I have. So there will be a balance between annihilation and expansion. Expansion will dilute, the annihilation will just remove them from the phase space. So you have to plug that in and find the final expression for the number density of particles as a function of time and as a function of the Hubble rate. So I'm not gonna go through all that. So I'm just using my notes I had when I was doing my PhD. Okay, so I will skip all that. I'm gonna do some magic jump to find this one. And then I'm gonna cover this, explain this in detail. So you're gonna see in lots of textbooks, and well, there are not that many regarding dark matter, and also in articles, scientific articles, that the dark matter annihilation cross section is expanded in a series of the velocity. Well, the dark matter velocity in galaxies and cluster of galaxies are a bit larger, but anyways, can be expanded in terms of velocities. Why? Because simply these velocities are small compared to the speed light. So the velocity of the dark matter galaxy, the dark matter particles in our galaxy, is they are non-relativistic, and they're around 10 to minus 3. The velocity, the speed of light. Okay. So the reason, so just to emphasize, I can expand because it's small. Okay. If dark matter, there are some models now in the literature where people are saying, look, let's say that some tiny fraction of the dark matter particles are relativistic when they are around. They're still relativistic around. So I have dark matter particles relativistic, and they comprise a small percent of the total dark matter abundance. If this is true, then their annihilation cross-section cannot be expanded in velocities because their velocity is large. You can only expand if they are non-relativistic. Okay? If they're relativistic, you cannot expand. And the whole way you can put the Boltzmann equation, again, will not be using as a cold relic. Will be in the same case as a hot relic as we did previously for the neutrinos. The only difference for hot relics is very easy to solve the Boltzmann equation because you just take the yield, number density over entropy, pick the time at which the freeze out happens, and then you plug in the temperature at which the freeze out, then that's it. You solve the yield. And the abundance is related to the yield. Okay? For the cold relativistic case, for the cold relic case, then you have to really solve the Boltzmann equation because there are non-trivial processes there should be taken into account. Okay, so let me just emphasize. The abundance of dark matter particles depend on the number density. Okay, let's establish this. The abundance is rho over rho critical density. And this rho for non-relativistic depends on the mass and the number density over rho critical density. But this guy here, as we've just seen from the Boltzmann equation, here, will depend on the phase space, and the number density of particles is a function of time, which is affected by the annihilation rate and the expansion rate. Can be diluted and can be also removed from the counting. So so you have two things, the expansion rate and the annihilation rate. And the annihilation rate of those particles, so you have chi, and finds chi produces something, whatever this something is. So I had two particles in the beginning and no dark matter particles in the end. Therefore, two dark matter particles are missing from my final state. So decrease the number density. In the early universe, however, it could always go back and forth. Let's say I have a chi bar annihilating to E plus E minus. In the early universe, I could have E plus E minus annihilating to chi bar. Because I have enough energy, I had enough energy for E plus E minus to produce back chi bar. Let's say chi bar is 1 GeV each. So in the early universe, at temperatures larger than 1 GeV, E plus E minus could produce chi bar. but could always produce E plus E minus because they have enough, well, mass to produce E plus E minus.
Usually the freeze-out mechanism is to stabilize dark matter. I mean, from cosmological perspective.
If the freeze-out is to stabilize dark matter?
Cosmologically speaking?
No.
Because you break some kind of chemical reactions?
No, the freeze-out is to have a leftover abundance of dark matter.
But at the same time, you are...
If you don't have a freeze-out, you just be the equilibrium yield and you'll go to zero.
Yeah, but in this case, you are having, I mean, you have production in sparkles.
No, but the dark matter continues to be stable. What dictates the freeze-out is just the symmetries that that particle possesses, not the freeze-out. So let's think of this way. Pick a model. So Jacinth is asking if the freeze-out is connected to the stability of the dark matter particle. So let's pick a model, and I make the annihilation cross-section extremely large. The final abundance will be tiny. The dark matter is still stable. Right? I can make the abundance to be, 10 to minus 8. Still stable, but the abundance is tiny.
Because you are saying that anyway, what will stabilize the dark matter would be the interactions. The symmetries behind.
Yeah, the symmetry. The interactions are consequence of the symmetries.
Okay.
Okay. Sure, there are masses involved.
But then look, if I have, in the case of the chemical coupling, we say this kind of process cannot happen anymore. So somehow I'm saying that dark matter cannot decay or produce something.
No, this has to do with mass arguments. So he's asking about the stability. So you're gonna see it just towards the last lectures that dark matter stability is dictated by the symmetries and its mass. Okay. For instance, an electron is stable inside a model. Is because of the symmetries. It's not just because of the symmetry. It's not just because of the symmetries, also because of its mass, because it's too light, right? So yes, sure, the symmetries can prohibit the decay, but the mass also has to be the lightest one. So that's why dark matter particles tend to be the lightest dark particles around for them to be stable. So for instance, there are dark sectors in which you have more than one dark particle, but the one that will be the dark matter is the lightest one, because the one that remains stable across the history of the universe. Right? So you have two arguments. One has to be the lightest or close to the lightest. Okay, there are cases that is not necessarily the lightest. Okay, the lightest, and by symmetry, preventing it from decay too fast.
By the masses.
By the masses, yeah. Sure.
Because in some cases you could have.
Okay. Okay. Fine.
Yeah.
For instance, the muon mass, if the muon mass was close to the electron mass, muon would be stable. Right? Muon is not stable because it's massive. But I say, okay, but could I change the symmetry of the standard model to make the muon unstable? Yeah, sure, but if it's the lightest, I don't care.
Yes. That's the point, because in the more root component dark matter models, you have to ensure that one of the particles of dark matter
is the lightest
one.
Mm-hmm.
There is a kind of bound in terms of the mass, as you said.
Yeah. Okay, so and now going back, so all this thing you can see right now in my screen is just the derivation of the final abundance for dark matter as a function of the annihilation rate. And here that's the formula that you typically is gonna see is the sigma v average. I'm gonna explain what average is. Is divided by, is written like this. So you have a first term, and the second term, and the third term. So the first term is typically called S wave. The The second term is called P wave. The third term is called D wave. So let's go through them. So the first term is called S wave. It simply refers to the fact that the annihilation cross-section does not depend on the velocity. The second term depends on the velocity. The third term also depends on the velocity, but in a power of 2. Well, when you square it, it will be to a power of 4, which is this term right here. So this term is called S wave. You can see from here. This one is P wave, and this one is D wave. So S wave is when you compute the annihilation cross-section. Look, I have the annihilation cross-section times V. And then I have one term that might not depend on the velocity called S wave. This one's P wave, and this one's D wave. But let's understand this. What is this sigma V average here? It's called the annihilation. We call it still the annihilation cross-section, but it's actually the thermal annihilation cross-section, but we just call it daily annihilation cross-section. But it's the thermal. What is the thermal? Thermal annihilation cross-section is simply the cross-section you know how to compute it. But then you have to integrate in the momentum space and normalize by the momentum space. But this momentum of the particle does have some scale factor dependence. So when the annihilation cross-section, the thermal annihilation cross-section, is simply the annihilation cross-section you know. So you learn in particle physics how to compute cross-section. And it's easy to plug in the relative velocity. Just know the velocity of 1, the odds at rest, then you know the velocity. But then you have to normalize, take into account that the annihilation cross-section of those particles are happening at different stages across the expansion of the universe. So in particle physics, in an accelerator such as the Large Hadron Collider, I have one particle with 7 TeV, the other one is 7 TeV energy, and that's it. This thing will not change. If I do it now, in 15 years from now, 7 TeV, 7 TeV. Well, the time scale is very small. 50 years, nothing for the universe. But at the cosmological scales, at early times, the energy you had was much higher than the energy you would have today, even if you pick the same mass and the same velocity of those particles. Because the quantity velocity they have, you have to also include thermal effects that those velocities, take a velocity of 10⁻³ at early times, that was not actually the velocity of the particle, was much higher, because it's like the thermal energy of the universe, the momentum that the universe provides to those particles is related to the temperature of the photons. Therefore, that's why I was saying that one E plus E minus can annihilate into 2 pairs of particles of 1 GeV. How is that possible? If electron impulsions have half MeV of mass, how can they annihilate into particles with 1 GeV mass? That violates energy. Well, it does violate energy today, but not back then, because then these particles had thermal energy, or kinetic energy, in other words, and they provided them enough energy to annihilate back into dark matter. The same way it goes for dark matter. I have a 1 GeV particle, dark matter particle, pairs annihilate into what? E plus E minus, muons, 1 GeV, and S quarks, light quarks, that's it. But in the very early universe, they had enough energy to annihilate into much heavier particles. B quarks, taus, and etc. C quarks. Okay? So depending on the temperature at the period of time at which those annihilations took place, the sigma V you find is different. Therefore, because the universe is expanding and the energy of the particles are changing over time, you have to account for the thermal energy or the temperature-dependent space phase of that annihilation. The space phase in particle physics is just the kinematics driven by mass and energy. At the universe, there is a temperature dependence as well, and you have to account for that. And that's what we call thermal annihilation cross-section. When you do take into account not just the energy of the masses of the particles, but also the thermal energy they had across the expansion of the universe. Okay? So that's what the sigma V means. The rest is calculation. All right, so have in mind, assuming that you understand what sigma V is, that's the key thing is understanding. The calculation, I'm sure that all of you will easily deduct all the formulas that I just showed in the notes. You're gonna do your homework. And the point is, just to emphasize that this sigma V, average sigma V, or thermal annihilation cross-section, is different from sigma V. It can be very, very different. In which sense? Well, I just showed you here. Let's go back. Sigma V, average, here, can be equal sigma V without the average if you have an S-wave annihilation cross-section. There is no velocity dependence. So in other words, I have one TV and one TV annihilated, produced, whatever. Even in the past or today, if it's S-wave. If it's P-wave, then depends, because there is a velocity dependence. So it's feeling the thermal energy of the universe. So in the early on, the sigma V early on was very different than sigma V today. Okay? Can be very, very different. And power of 2, where? No, it's just, it has to do with the, here, I'll go back. Let me write it. It's when I write the energy as a momentum squared. In the non-relativistic case, that's where you get a V squared. Okay? P squared over 2m, that's where you get the V squared. Okay, he was asking why appears only powers of 2 in the velocity. It has to do with the definition of the non-relativistic energy, which is P squared over 2m. So, okay, so in the end, so that's what I want you to show. Is this formula. So this, there was a, I said that I want the Boltzmann equation for the hot Rayleigh case, the cold Rayleigh case. That's what the past lecture is. And for this lecture, I want you to solve this equation right here, which I'm going to cover right now. So once you plug in all those numbers, you get the number density. This n dot is the dn dt, derivative in time. 3h, h the expansion rate, and the number density. Sigma v is the thermal annihilation cross section. The neq is the number density at equilibrium, minus n squared. N is the number density without imposing equilibrium. What's the difference between the two? Is that one has a chemical potential, the other doesn't. Okay, that's the only difference. So one has exponential of minus mu minus m over t, and the other has a mu, the other doesn't. Okay. Okay, and I'm using this formula that's very easy to derive. And again, I'm going to rewrite. So that's the formula you're going to see in all textbooks. Okay, this one. And then using the definition of yield n over s being the entropy density, n being the number density of particles, you can rewrite that equation in this way. So look at this. Remember, y is just the yield, the number density divided by the entropy density. And this function, the yield, I'm going to plot the solution of this equation as a function of x. X being the mass over t. So that's the plot you're going to see in many of the papers. I like this plot. It's really clear to see and understand. Look at this. So remember, y is related to the number density. So what occurs is, here we are in the early universe. At early universe, you have the number density of particles is roughly constant. Why? Because I have chi bar produces E plus E minus. But then E plus E minus produces back chi bar. So the number density of particles is not changing over time. Because I have two, I lost two because they produce E plus E minus, but roughly at the same time, E plus E minus produce back E chi bar. So the number change of particles is constant. It does not change. Well, it's normalized, see? So it's just a constant. Why is a constant? Well, because y is not exactly equal to y when x is equal to 0. So there's a difference. Remember, I'm just taking the number density divided by a different number density. If they are basically the same up to a constant. And that's what the constant is. So if I had to plot just delta n, the number density of particles, delta n, how much would change over time, this would be starting from 0 here. If there was delta n here, chi, this will start from 0 because there's no number change. There's no change in number of particles, okay? That's what it means. Fine. Okay, and then the universe is expanding. The universe is expanding. And you saw that the number density of particles is proportional to minus m over t in equilibrium, right? There's a mu term, but okay. In equilibrium, that's the curve in blue. So it's being Boltzmann suppressed depending on the mass. Remember, this is x, right? X is here, see? So it's decreasing with x. I increase x and goes exponentially decreasing the number density. However, and it will decrease, decrease and decrease and decrease. Up to some point, we'll reach 0. 0, right there. So if dark matter particles remained in equilibrium across the entire time, the number density of dark matter particles today would be 0. There would be nothing left. Okay. And now what happens? What happened is I have some whatever, for instance, how many dark matter particles I had in the very beginning? I don't know. You have to give me a model and tell me how this initial density of dark matter particle was created. Typically people assume it was from inflation. So they inflate on decay and produce some dark matter particles. Okay, fine. I don't know, 10 dark matter particles in the beginning. And then they were in equilibrium. Fine. They remained in equilibrium until today. How many there are left? 0. Nothing. Exponentially suppressed by their masses. Okay? The more massive they are, the fastest they go to 0. But however, if they are light, regardless of the mass, okay, they'll go to 0 if they are remaining in equilibrium. However, the universe is expanding. So they are decreasing, 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 decreasing the number density, the universe is expanding. At some point, the chi bar will no longer have time to find each other, and the universe expands before that. They try to find each other, the universe expands. They try to find each other to annihilate, the universe expands. At that moment, from that moment on, which is called freeze out, that moment is called freeze out, the dark matter particles have no longer time to find each other and annihilate. When that happens, whatever was left from the 10, maybe it was left, 5, 3, that 3 will continue until today. So that's the leftover abundance of dark matter particles that we measure today. Okay? The ones that were left after the freeze out. So if the freeze out is here, this point here, XF, so that's what's left. And as you see in these horizontal curves, is what I'm showing is, if the annihilation cross-section is very large, 10 to minus 10, it's too large. In other words, it's saying that they happen really fast. So if they happen really fast, it took longer for the universe to catch up with the annihilation. So they continue to decrease and decrease and decrease and decrease and decreasing, and the universe caught them. So, okay, now you will no longer find each other. And that's left. There's something left. So there are fewer dark matter particles around because the universe took a longer time to catch the time at which those annihilations took place, to equal the interaction rate, or to equal the time at which the annihilation needs to occur. Okay? So the annihilation rate, let's say, needs 1 second to occur, and the expansion of the universe takes 5 seconds to happen, the annihilation rate will occur because the universe takes 5 seconds. At the moment at which the universe takes less than a second to occur, then that annihilation will not occur anymore because the universe has expanded before that. So they are trying to find each other. Remember, expansion means spreading time, right? Now I'm blanking the word. Man, I'm blanking the word is rubber when you're stretching. That's the word. Stretching the space. So you have two parts, then you stretch the space and they move further away from each other. So they no longer have the time to find each other and annihilate. So the larger the annihilation cross-section, the smaller the abundance. That's why the abundance of cold relic is proportional to 1 over sigma V. But the larger the annihilation cross-section, the less you have. Okay? It's inversely proportional. Okay? All right. And as you see, from this plot, what happened is the number density today, the yield today is called yield infinity. It's just today at some time, infinity, very large time later, is roughly the yield at freeze out. When you do solve the Boltzmann equation, there is a small difference between this point here, freeze out, and this one. See? There is some small difference. That small difference is called a constant. So that's what you do it when you solve numerically. You realize that the number density of dark matter particles today is a bit different, smaller, than the yield at precisely at freeze out. Okay? All right. So you solve it. And what is this yield at freeze out? So this yield at freeze out would be if I took N equal N freeze out over entropy. What is N at freeze out? Some constant, M pi 3/2 something, exponential minus M T freeze out. If I plug in this number, that would be Y freeze out. Okay? If I plug in that number, so this number, I compare this number with the one I actually get solving the equation, they're a bit different. So if you want to have just an estimate for the relic density, you don't need to solve the Boltzmann equation. You just use this formula of Y freeze out, divide by some 2, constant factor of 2 or something, you're going to get roughly the same, the correct dark matter abundance today. I mean, the correct value. Okay, so if you do a more precise estimate, so that's what I'm not going to go through this because I want you to do as an exercise. So I just now do it more properly where I plug in the yields for everything. This I'm solving explicitly the Boltzmann equation, so I'm not going to go through that. Hold on, then I find this formula. So that's your whole exercise, okay? Find this formula, find it. That's your homework. So you get the abundance of dark matter particle, omega h squared. Where does h come from? H is simply the error embedded in the measurement of the Hubble rate, or the Hubble constant, sorry. The Hubble constant, H naught, is equal to 100 H kilometer per second per megaparsec. So H is the error. That H is this H right here. Okay? Which is around 0.60 something. And most of the cosmological parameters are written in terms of h, because an error, then you propagate the error across all the cosmological parameters. But what I want to emphasize here is that here it is. The annihilation rate is in the denominator. Okay? But what is important? So I want to remember. So the key things here is that sigma v, key things of this lecture was that sigma v is proportional to some factor which does not depend on the velocity, and some other factor that depends on the velocity, function of v. This is called S wave, and this is called P wave. Okay? The other one is D wave, but it could be called P wave. It just means there is some velocity dependence. Okay? So the annihilation cross-section could be S wave and P wave. What I'm saying is, now we're gonna go through the real physics of dark matter. So let's say that I'm pointing using a telescope, as many of the guys here are from São Carlos. You guys search for gamma rays using CTA data, Fermilab data, SWGO, whatever. So you're pointing at a sky, you're observing gamma rays, and you can constrain the dark matter annihilation cross-section. Because the more dark matter annihilates, produce gamma rays, the more flux of gamma rays I see, then I can constrain what the cross-section should be to be consistent with the data. But if you're measuring gamma rays today from our galaxy, or from a galaxy cluster or dwarf galaxy or whatever, which sigma v I'm constraining? I'm constraining the sigma v today, which can be very different from the sigma v at early times. If the annihilation cross-section is P wave. If it's S wave, it's not the same. It is the same. Okay, if it's S wave. Fine? Okay, and that's interesting because as far as indirect detection goes, you can constrain sigma v today, and you can also constrain sigma v at roughly early times. Not so early, but roughly early times.
So in this case, it depends on the distance of the source that you are looking.
Yeah. So yes. So for instance, if you observe gamma rays today from a galaxy, you constrain sigma v today. If you use CMB data to constrain dark matter annihilations at CMB times, you constrain sigma v at early times. But it's not so early because dark matter froze out at, I don't know, 10 GeV. That's way before the CMB last scattering surface, way before. So even using CMB data to constrain dark matter annihilation, you're not really probing the same sigma v that governs the relative density. They are independent things. See, can be very independent. So it's not, why I'm saying this, because you're gonna see lots and lots of people. I want to add this today because this is very important. You see lots and lots of people who don't know, didn't study much dark matter. Let's try to be more polite. Didn't study much dark matter. Come on, I want to A4. Yes, add pages. They didn't study much dark matter, and look what they do. So they see a plot like this. This is sigma v over the mass, m chi. And there is a limit, let's say like this, excluding everything above. And there is a line here which is called like this. So this line here is 3 × 10⁻26, okay? Centimeter cube per second. Okay, they did not study much the theoretical aspect of dark matter. So let's do it. So here, let's say this crossing happens precisely, this point here appears at 50 GeV. 50. Everything above is excluded. Then what you're gonna see a lot in conferences, at high-level conferences, people saying, well, we have excluded dark matter particles, thermal relic, for masses below 50 GeV. What? No. sigma v, let's first recap. Sigma v could be let's call it like this. Let's say let me be even more, sigma v, let's say is roughly sigma v, but could be something else, sigma v, times some function of velocity. Okay? Let's rewrite the sigma v I had, let me write below, even smaller. So what I had was sigma v was roughly a plus b v squared, right? So I'm going to rewrite this like this. Sigma v as roughly sigma v plus sigma v times some velocity function. Okay? Since something depends on the velocity. It's related to sigma v, but I don't care. It's not the same, but it's related. Now look at this. So even if it is this case, sigma v is roughly a, then if it is this case, and the dark matter n, let's first assumption, is S wave, fine. Then sigma v average is roughly sigma v. It's not exactly the same, but okay, but basically the same. Okay, and then if you also assume that sigma v, just annihilation, drives the abundance, because you're going to see later, there are other processes, as he's going to talk on Wednesday, even if Patricio will talk on Wednesday. There are other processes that can drive the relic density besides sigma v. Okay, so that's assumption one. If sigma v thermal is equal to sigma v, if the annihilation implies into the dictates the abundance, if both cases are true, and third, that is no entropy injection, episode, then they're right. If the dark matter particle is lighter than 50 GeV, then it's true. Dark matter has been excluded. Thermal relics has been excluded. If the three assumptions are correct. But it's not at all general. Okay? So this one is not, this one appears in many models. This one not so much. And this case here, so you see, in order to make this statement that I exclude dark matter particles below 50 GeV, embedded in that conclusion, there are three assumptions. I know this, for experimentalists, this sounds, what? No, my experimental limits is data. I don't care about the assumption. Sure, you care about my assumption. Because you're overlaying experimental limit under some model. The flux is experimental data, period. When you call sigma v average equals sigma v without the average, you're already making an assumption. Okay? Just so you make an assumption no matter what. You make an assumption. The flux experimental data, nobody will question it. But from correlating flux to sigma v average, you have to make an assumption. When you plot in this plane, you are making an assumption. And depending how you phrase it, if you say exactly everything below 50 GeV, then you're making three assumptions at the same time. One is that sigma v drives the relic density, because look, there are models, as we're going to see later, that the annihilation rate is not governed, the abundance of dark matter particle is not governed by annihilation rate. The CTA thermalite will constrain the sigma v, but the annihilation, the abundance is not dictated by sigma v, it's by something else. Therefore, you cannot say that you ruled out everything below 50 GeV because you haven't. Okay? You haven't. This does not undermine the search for dark matter using gamma rays. Does not. but I'm just want to get the facts straight. Okay. Having a bound like this is important. It's fantastic. If we see a signal, we're gonna celebrate. However, we cannot claim that we excluded dark matter particles below 50 GeV when you see a plot like this. Okay? Sounds good? Awesome. And then we finish for today. Okay, I finished in time today, this time. So you have some homework to do. And the next lecture, we're gonna cover some other aspects of dark matter abundance, which are the exceptions to the dark matter relative density. So far, I discussed the annihilation, okay? And we're gonna cover other possible ways to produce dark matter through coagulation and other processes, okay? Forbidden channels and so on. All right, guys. Is there any question? Could be one of those as Jacinto presented last lecture on. It could be a Z2 symmetry or so on. But any symmetry, for instance, let's say if you think of the standard model, you have baryon number, lepton number. There are symmetries, global symmetries in the standard model. They could also be responsible for stabilizing dark matter, if dark matter does have lepton number and baryon number somehow, because B and L are conserved in the standard model. If they're somehow not conserved, they are gauged symmetries of the standard model, for example, a new theory, then they might be as well the symmetries responsible for making the dark matter particle stable. Okay, so symmetries. So the way you do it is not easy to see, but it's like it's like in the standard model. We impose a symmetry, right? SU3 color, SU2 left, U1 hypercharge. You impose this from the very beginning. Then you write down the Lagrangians that obey the symmetry, right? When you write down the Lagrangians that impose the symmetry, you see from that Lagrangian that the electron cannot decay, right? Because, okay, it's the lattice, but it cannot decay. If we're too heavy, then it would decay, like the muon does. And then you say, okay, what is making the electron not decaying? Is the SU3 color, SU2 left, U1 hypercharge, plus its mass being light. So those are the symmetries that are responsible for the electron to be stable. Okay?
When you take cross sections and velocity in an function in terms of velocity, and then you write the thermal cross section of temperature, you're using the theory
Yes.
to relate velocity and
Assuming it's a Boltzmann.
assuming, okay.
Yeah, so he's asking how I can relate the temperature and the velocity when expanding the velocity series, the thermal annihilation cross section. How can I expand the thermal annihilation cross section in terms of velocity or temperature? I'm assuming that the dark matter has a Boltzmann, which is for non-relativistic gas is a very good approximation, right? So the Boltzmann. So if you assume a non-relativistic gas, so it's okay. I don't go to Bose-Einstein from Dirac statistics. I just go to Maxwell-Boltzmann, to the Maxwell distribution. That's fine. It's easy. Maxwell-Boltzmann. And then so I assume that, then I can relate the velocity with the temperature. Okay. And that's why, for instance, you can relate how much energy that particle had at some point in temperature. Because the velocity was not just v, depending on the temperature. See? So that's why it has different annihilation cross sections depending on the temperature. So today is one temperature. Our early time was a different temperature. So the sigma v was naturally different.
Like it would be, they're going Hubble
Hubble expansion. It was feeling the Hubble drift. Yes. the expansion and drift. Depends on the model. Yes. So you cannot see it at first hand. So, I see here is the velocity is going to appear. You can't see it. You have to really compute it and see that what happens. You have to compute it. From experience, I already know. Yeah, the ones that give rise to velocity dependency, which are the ones that are proportional to gamma 5, where the quarks, so you have chi bar and QQ bar, let's say, or fermion and anti-fermion. If there is a gamma 5 between the fermions, they'll give rise to a velocity dependent cross-section. If it does not have a gamma 5, you'll just be S wave. For instance, if you have like the beta decay. Remember that we had a Fermi wrote down an effective operator to describe the beta decay. So you have chi bar and let's say QQ bar, or fermion anti-fermion, psi. So if I put in chi bar, whatever, it won't change much. But if I put it in between the fermions, for instance, I have gamma mu, which is a vectorial interaction, you'll be S wave. If I put gamma mu, gamma 5, we'll have both. Whenever there's a gamma 5, you induce a velocity dependent cross section. But sometimes it's not the most relevant one. Okay, so if you have gamma 5, so axial interaction for the fermions and vector interaction between the dark matter particles, they'll lead to a S wave and a P wave. But the S wave will govern the relative length, the sigma V. If you have gamma 5 and gamma 5, it's velocity dependent. If you have gamma 5 and gamma mu, it's velocity dependent, you have both. Always when there is a gamma 5, there is a velocity dependence. Depending on the structure of the vertex, we'll find an expression that might be driven by P wave or might be driven by S wave. So it depends on the model. Okay? And it's funny to see that what is a gamma 5? What the heck? That's what a gamma 5 has anything to do. So when you do the traces, some of them will depend on the momentum, some of them won't. So the amplitude, when you compute the amplitude, some of them will have a momentum appearing, and the other ones won't. And the momentum is related to the temperature or to the velocity. That's how you get the velocity. So it's the structure of the amplitude at the end of the day, which is dictating whether it will depend on the velocity or not. Okay, when you compute the m squared, amplitude squared.
How does it come up with
I assume. So he's asking how the gamma 5 will appear in the amplitude. So it depends on my theory. So in the standard model, we have the neutral current has both gamma mu and gamma 5, right? So there will be a term that will be proportional to gamma mu, and there will be a term proportional to both gamma mu and gamma 5. And one just gamma 5, depending on the fermion you're taking, the chirality of the fermion. If you may also have a theory beyond this standard model, like the Higgs is just is just a constant, it's just the identity. There is no gamma 5 in the Higgs. The Higgs is a CP even scalar. But there are theories beyond the standard model where there is a new Higgs. And the new Higgs field is a pseudo scalar, which does have a gamma 5. And then where the gamma 5 will come from. So it depends on the theory beyond the standard model in which your dark matter model is embedded. It might change the nature of the particles. So for instance, Mariana particles cannot have purely what? Let's see if you first could I have a Mariana particle with let's say chi bar C bar gamma mu chi. Could this chi be Mariana? Yeah, put C in the first one. Yeah, C. Yeah, could I have a Mariana particle with this? I'm asking this. Let me write what Jacinth is writing the board. So could I have a term like this? Chi bar C gamma mu chi being Mariana field?
But in this case, it would be
Could I have it?
You would have a Z.
No, I can't have it.
Then you would have a Z.
Why I can't have it? Because vectorial interactions are electromagnetic interactions. And Mariana particles cannot have electric charge. So, for instance, if Chi was a fermion, a dark matter fermion, a Majorana fermion, dark matter was a Majorana fermion, it could not have that charge, that interaction. Mm-hmm. Okay. So I could have Chi1 and Chi2, different particles, but not Chi1, Chi1, or Chi or Psi or whatever. So Mariana particles do not have, cannot have vectorial interactions. Cannot. They can have a term which is gamma mu, gamma 5, which is called a dipole moment interaction. Okay. So remember, electromagnetic interactions means related to electromagnetism. And then the electromagnetic interactions are proportional to the electric charge of the particle. And a Mariana particle cannot have electric charge. Therefore, Mariana particles cannot have vectorial-like couplings. Okay? Because Chi is equal Chi C. So if neutrino, for instance, they can E plus. Could E plus be equal E minus? No way. I'm just applying C, the charge conjugation operator. So Dirac fermions cannot have terms like this, or Mariana terms. Mariana terms cannot have vectorial interactions. Cannot, because psi is equal psi C. Okay. Make sense? There's a lot to take in.
I thought it was more related to biology, because of the vectorial parts.
But okay, I need to go. Okay, guys, I see you on Wednesday at 9, okay? Is that 9 on Wednesday? Because I have to teach at around 10:30. I have to leave on Wednesday. So on Wednesday at 9, I see you all, okay? Bye.